You can start, sir.
You're able to see my screen as well. I've just opened it up. Can you confirm?
Yes, sir. I can see.
Okay, perfect. Uh, First of all, thank you everyone for joining today on the Data Hour, and pleasure to be part of Data Hour and present today. So I'm going to present on data preparation and feature engineering in ML. As we discussed some of the topics that I'm going to discuss. One of the thing is we might not get enough time to do a practice problem, and that could be a follow-up session. But I want to cover up all the key important aspects before that practice problem. So what we're gonna cover today is the ML foundation, how we can do the problem framing, and the steps for data prep. Uh, Within the ML problem framing, we will be discussing about how understanding the ML problem and framing the ML problem, and then what goes into the data prep and feature engineering, in which we will be covering how we would be constructing or what considerations we should have in constructing the data set and transforming our data set. This is a course which is also taught by Google. If you go to aigoogle.com, it's a really good course wherein they have all the details as well. So I thought this would be a great segue before anyone delves into any ML, because sometimes we get into a habit of doing all the jazzy stuff, ML stuff that we want to do. We hear all these terminologies, but these are like basic steps, I would say, that we miss out on that are required before we delve into any ML problem or do any kind of modeling or jazzy stuff. So, uh, you've already heard some intro about me. So I'm Rishabh Dhingra. I'm currently working with Google Canada, a solution consultant in the analytics space. Uh, I have around 11 years of experience and have led multiple global data analytics and data science teams. Uh, and I've also helped build the team at Inflection Analytics. It was kind of I was a co-founder there. It's a startup of analytics back in India. Uh, in my free time, I run a podcast called Inspired, where I interview people focusing mostly on data science, analytics, and product leadership. Okay, so we can delve into the topic now and start with the ML problem. And I want to take through the process first. I mean, at a high level, if we split the process, the entire ML process, and it can go beyond this as well. But this is a simplified way of breaking down the ML problem into a process. So we start off with defining ML problem, and then what will be the solution of the problem that we are trying to solve, and then preparing our data sets to build models, uh, and then we transform our data and make it in a format that is ready to build models, because the raw data, as we know, is not ready to train models on, right? So we need to do some transformations to the data, and then once that is done, we can get into training the model. Once the model is trained and we have tested it, we are happy with the key metrics of the models like accuracy, you see whatever we are testing based on that, and then we put that model into making predictions, and then improve the model, review it, and once the model is there, as I said, you can expand this. You continuously monitor as well for some things like data skewness, uh, and as the data sets will keep on changing, you keep monitoring if your model is still working fine, or do you need any tweaks. So that's a typical process of an ML problem. uh, what we're going to discuss today is first three parts, which will be uh, define a ML problem and propose a solution, and then construct it and transform the data. So these are the three things we're going to discuss today. So within the ML problem framing, so problem framing is what that helps us determine, what's our technical feasibility of the project. And when we have to define clear goals and success criteria, that's where the problem framing, that's what it is, problem framing. And when we think about an ML solution, and an effective problem framing would actually determine whether you would succeed or not succeed. Because in my experience, I've seen a lot of scenarios where we've gone right away into capturing the data, transforming it, building the model, showing the results. But working closely with business, you later realize, oh, you've built this, great model, but it's not actually solving the business problem that it was intended to solve. And also the business is not too happy, say, with what the model is achieving. So, and so what you have done is like you spend all this time doing all this hard work, and then, but it doesn't solve. So the model is just sitting there, not even in production. That's why this is really key step to understand the problem, and do the problem framing. So it basically has two steps. So first thing is we have to determine if actually ML is the right approach for solving a problem. You do not need ML in all the cases. Some things could be done without ML as well. So I've seen people like anytime the problem is there or data problem, the first approach is ML. That's not always the case. You have to think of there is cost to building the ML model, there is cost to maintaining it, and what benefits it's going to give. So all those things need to be considered before even thinking if ML is even the right approach. Once we have discussed or finalized it, yes, ML is the right approach to solve a problem. Next come is how do I frame my problem in the ML terms, and we'll discuss these in details. So in short, like problem framing is helping us in ensuring that the ML approach is a good solution before we even get to the work and start doing the data and training the model. So there are two aspects of it. Stating the goal when we talk about understanding the problem. So we have to state the goal uh, of the product. So by what do we mean by stating the goal? And this is purely in non-ML terms. Forget about any ML terminology. The only thing we are trying to answer here is what am I trying to accomplish? So ML generally is, is a specialized tool. Is using this to solve particular problems. And as I mentioned earlier, you don't want to implement complex solution when there is a simpler non-complex or non-ML solution that will work, right? So you would think of quality. Say how much better do you think my ML solution can be? If it's just giving me small improvement over what I currently have, then you think, okay, maybe the current solution is already the best one. I don't need ML solution. As I mentioned, cost and maintenance, that's expensive, right? To build and to maintain. So is it justified that my ML solution, the cost increase that we will incur, is that justified with the ML solution? And how much maintenance is required? Because it requires long-term maintenance as well. As the data would change, you would need to, keep on looking at your model and reviewing your model as well. And people need to support as well. So you need to hire people, you need to train people with ML expertise. So all that needs to be there. So all these things need to be taken into consideration. So these are the two things I would focus on when understanding the problem, stating the goal. And these are some of the examples, right? So the goal in a very simple term is for a video app, we all know YouTube. Uh, the goal is to recommend useful videos, right? But what you're trying to accomplish is here defined in a very non-ML term. It's purely business term, right? If you think there's no ML solution, what are you trying to accomplish? We have food delivery apps. We all use like Food Panda and Swiggy, right? One of the features that someone is building on the ML team or in the product team is I want to calculate the delivery time accurately. So they're clearly defining what they're trying to accomplish. and not telling you how they want to accomplish, whether it's through ML or non-ML. That's the latter part, right? That's something that will come later. But in very simple business terms, what we are trying to do. And then you see, okay, to solve this, whether the ML is the solution. If food delivery time is being calculated heuristically, not through ML, is it accurate? Are we like 90% accurate? Maybe yes. Then do we need ML if it gives us 91% accuracy? Maybe no, right? So that's the second part, use case of ML. Maybe the cost and quality is does not justify the use case for ML. Uh, Next is like obviously with any ML problem, you need a lot of data, right? It's all data, ML, AI, it's all training on a lot of data, and data is a driving force. So to make any good predictions, you need the data that has features which gives you great predictive power. Only then you'll be able to get benefits out of your model or your ML solution. And in a broad way, we should look at some of the characteristics of the data to ensure we have the right data that is required to even proceed with an ML solution. So data needs to be in abundance. So you need to have relevant, useful examples in your data set and more examples. So if it is abundant, you have more examples, you have relevant examples in your data set to be trained on, the better your model will perform. It needs to be consistent and reliable. So you cannot have data that will, in your production system will not be there, or you will have like missing data for 80% of scenarios. So that's not consistent and reliable data, right? So you need to use the data that is collected reliably to produce a better model. And taking an example like weather based model, so you have data that is gathered over many years, right? From systems which are like tested thoroughly and they are in production thoroughly, and you're getting data from those reliable systems, so you can now rely on that data to be used for your model. Next is data needs to be trusted. You need to understand where the data is coming from. uh, would you be Can you trust those data sources, or you don't understand those sources at all, and you doubt their reliability, you doubt the source of data, uh, or is it or the data is actually coming from another ML system which might break in the future. So those are the things you need to consider, what kind of data you have at your disposal. And the data needs to be available. We need to make sure that the inputs are available at a prediction time, as I mentioned, that you're not collecting something when you're actually putting the model in production. Those data points will not be there. So think of certain features that you're going to select in your feature engineering. Are those features going to be available always? If not, you better you're better off omitting those features and not have it. Next is correctness. I mean, accuracy or data challenges are always going to be there. Like there are no data sets which does not have these challenges. It's inevitable. So there are some labels that would be incorrect. There are some values that would be incorrect. So we need to see what's the percentage of those kind of scenarios. If the percentage is high, your model is going to produce poor predictions. So you're better off doing that due diligence first than building everything and then later on realizing. And data needs to be representative uh, of the real world as much as possible. So the actual events that are going to happen, how the data is actually going to come. Are we covering all sorts of scenarios? Are we covering if I'm getting data for employment? Am I getting data for all genders, right? Because if I'm just getting data for one gender, it's not representative. And I'm not going to get accurate results when it's actually put in production where I would see data from employment data from all genders. So those are some of the things we need to consider. And as I mentioned, if we don't get the data in the right required format, or it doesn't, you know, have these qualities, we'll make poor predictions. And for any like good predictions, the features that you select, features are actually the fields on which your model is going to rely on to predict something, right? The values are the features on which the model will rely to predict. Those features should actually have good predictive power as well. So when I say good predictive power, it means they need to be correlated with what you're predicting. So let's take an example. If I'm taking a weather data set, right? A cloud coverage or a temperature or say dews would be better predictors of rain, rather than having like what's a moon phase, what's a day of the week. Day of the week might not give you any prediction of rain, but yeah, like temperature, dew point, those things would tell you. So that is what I meant by predictive power. So those features would have good predictive power. And also, you need to ensure that the prediction that we do using your ML model is actually converted into an action as well. That is going to help users. So what I mean is like the product that you're building should actually take inputs from ML and put it into some decision making. So model output gets converted into a decision making process, right? Uh, let's take an example like you have a you we were discussing about videos or YouTube, right? Whether a user will find a video useful uh, or not, that should be fed into an app that recommends the videos. If I just build a model and there's no action coming out of it, then there's no use. So you need to first define, which is pretty much defined by the state that we were discussing in the previous slides. What's your goal, right? So those are like a few key points I would say on the data side. And after you have stated the goal, right, then and understood that okay, this is actually an ML problem that you need to solve, and you've verified that it is going to be best solved using ML. Your data will be there that you need for modeling, and it adheres to all the aspects that we discussed earlier. Now you're ready to move to the next ML stage, that you will be now framing your problem in ML terms. So how you do that, there are basically three aspects of it. You do that by defining the ideal outcome and the model's goal. So for example, your food delivery app, uh, we wanted to like know the travel time, right? The ML problem would be we want to predict how long it will take to travel from the food to travel from restaurant to home address. In case say of a banking app, we want to predict if a transaction was made by the card holder or is it a fraud or someone else, right? Or in case of mail app, we earlier discussed spam and not spam, but what's an ideal outcome, right? We want the model to warn the user if the email appears to be a spam, right? So this is pretty much in line with state the goal section that we discussed. So it is the exact task you want your product or feature to perform. Uh, and based on the model's prediction, as we discussed about action, your product or your app want to take a decision. So if your prediction is, in case of classification is category A, then do X. If the prediction is category B, then do then take the decision B. So things like that. So it needs to be tied to a decision. And the model that you choose would be basically dependent on your problem statement, right? Whether it's going to be a classification model where you are predicting categories, which is like same as whether the email would be a spam or not spam. It's an example of classification. And Or it's a regression model. Regression would be whether if you're predicting a numerical variable, right? For example, number of views a video will get. If you're predicting that, that will fall into a regression model. So depending on what you're trying to solve, you'll choose the right type of model. And when you're doing that, there are like two big key consideration I would say you would uh, take into your mind is predicted decision. So whenever possible, you have to predict the decision your app will take. So in case of video, right? So for example, I'm trying to see, say, how much cache, how I want to cache the videos that are going to be asked more often by the users, or those that are more popular, and I want to quickly serve that to the user. And I could solve this through a regression or maybe through a classification as well, uh, because it's how you want to approach the problem. Maybe I calculate the number of views I'm gonna get, and based on that, I find out, okay, if the views are like 50 to 100, I use this cache. If the views are like 100 to 200, I use cache 2. If the views are over 200, I use cache 3, something like that, right? But again, the number of views is what you're predicting, so it looks like a regression model. But you'll have to see, like, if that gives you the same loss that the loss or the prediction that you need, whether that will help you take the decision or not. So in this example, if I classify the videos into cash, no cash, or expensive cash, right? Those are the decisions. That's what I meant by predicting the decision. So when you choose the model, you first need to know what you're trying to predict, and based on that, it will help you decide what kind of model you need to go for, whether it's classification or regression. And obviously, with every model or every problem, there are constraints as well. So you need to keep note of those constraints. So, for example, taking this example of cache, there's there's some value of views. You say above 50 is this, but how do you come up with those 50? 50 as your threshold. Is that threshold going to change from 50 to say 70? When you have more viewership, maybe 50 becomes a normal view number, and 70 is the new normal, right? So the threshold might change, which means it's a dynamic. So in those cases, you would end up with a regression model, or you'll effectively use a regression model. But then there could be fixed. If you say no, 50 is what it is, and it's not going to change, then you might as well use classification model. So some problem constraints is what you'll keep in mind when you are deciding on the model as well. So this is part of framing the ML model, right? And then you'll also have to look at identifying the model's output. So the model output is the labels that you would say, and that output will actually accomplish the task that you have defined in the previous step, right? So there are different models as well. So let's take an example of video app, right? Your ideal outcome that we want is that we want to recommend useful videos, but how do you define useful videos? We're not sure. We don't know, right? It could be, do we have a flag which where I can say it is useful or not? Maybe I'm collecting that data through the app where the users actually, every time they see a video, we flash a screen. Did you find it useful? Yes or no? That means for every video watch, you're collecting that data, which we know is not possible. If you're doing that, then you have the label, which is like, is was it useful or not? And it's a very clear label that you can predict, right? But that's not going to be the case. We all use YouTube. We don't get that, right? YouTube doesn't know like if this is useful or not directly. There are no direct labels. But that's where it comes. There's a concept of proxy labels, right? How can you assume that the user found the video to be helpful, right? So that's where a proxy label could be if the user shared it, if the user liked it, or it could be like the length of uh, uh, or the time the user spent on that video. Did the user completely finish the video? So those are like some of the proxy labels, which are basically the substitute for labels that not are not even there in the data set. And these are, as you can see, necessary when you can't directly measure what we want to predict. So there are a lot of real world scenarios where the companies or the product teams are using those proxy labels to measure the product performance because they don't have direct labels available for them. But we have to understand that no proxy label can be a perfect substitute for your ideal outcome. So they'll have some pitfalls, they'll have some problems. So you have to pick the proxy label that has the least problems for your use case. Uh, and then so that's like how you would go about with identifying the model's output. And the next is defining the success metric, right? Uh, so you have to define some metrics where that will help us determine whether the model is implementation is successful or not, right? I mean, these are not always the metrics that I say, like from the model perspective, like a data scientist would look at. What's the accuracy of the model? What's the precision or a recall or a RUC? Like these are like model predictors, right? Model evaluation metrics. But there are business evaluation metrics as well. So success metrics should actually define from a business perspective what you care about. Like, is it engagement, or you want to take help the users take some action, like fill a form, or as simple as watching videos that they find useful. Uh, at the end of the day, you want your model to help you move closer to your definition of success, right? Uh, and there could be cases that when you're analyzing the model performance, you would see, is it helping me move closer to my defined success criteria or not? If not, are you able to evaluate that? Can I improve the model and it can help me get closer to my success criteria, right? And how do you define when you want to improve the model? Maybe model is not good enough, but you want to continue. If that's the case, I mean, your model shouldn't even be used in production, right? But over time, can it be significantly improved or not? If it's not good enough, but you can continue. If the model is good enough and you can continue, then that model should be used in production and it should be further improved as well. And if your model is good enough, but it cannot be improved further, you have tried everything, that's the max performance you're going to get out of that model. Then you just have that model in production, but it's probably good as how it is now. And the fourth would be like if your model is not good enough, and it'll not change as well. So in that case, your model should not be in production environment, and even if you keep training, retraining again, it'll not get better. So, and there are resources that would be applied in considering the model uh, uh, to improve the model, right? So these are like some of the considerations when you are building the success metrics, and I've given some examples of how you could define success in a business term, which is, say, on a YouTube side, users spend on average 20% more time on of the day of their login sessions on the videos, and failure would be nothing changes, user is spending the same amount of time. So those are not like model success metrics, these are business success metrics. And now you can like come up with what are the actual model evaluation metrics which will tie to the success. Okay. So that was all about like model problem framing. It looks very simple, but trust me, this is the most difficult part when we start. Not most time consuming, but most difficult. Time consuming, as you all know, is a lot of majority of the time on ML project is spent in constructing the data set and transforming the data set. But problem framing is a very critical step, and I've seen in my projects that I've worked on as well is uh, ML models or initiatives failing because these steps we fail to perform these steps in the initial phases. So we have discussed about defining ML problem and proposing a solution. Next step would be constructing the data set. And I mean this model has this framework, as I said. I mean it's not fixed, right? But this is a typical framework you would follow. Uh, and in the construction of data set, like ML problems are all dependent on data, as we all know, like finding patterns, prediction, and then doing predictions. Uh, so we need to ensure that we have right data and we construct the data. This phase is done thoroughly, um, so that our models work like charm, right? And in the in the phase of construct data set, these are some of these steps you would perform, like collecting the raw data, then identifying the feature which on which the label is dependent on the label, what are the sources of the information, what's the sampling strategy you're going to use. Then you split the data, and then after that you transform the data where you clean the data and do feature engineering, right? So it shows that these two parts, as we're going to discuss, shows a typical process. But as I mentioned, it might not be ideal for every project, right? This primarily applies to linear regression or neural nets, right? But it's not even sequential, right? In some cases you might split your data first, or split your data after you have transformed it. So it all depends, like, on the use cases. In some cases you need to collect more data, or you need to modify the feature set uh, even after training has started. So it's a learning process and depends on case by case, on what works, what doesn't, right? So these are the two things we're going to discuss in the next section. uh, so let me move to the next section. So collecting the data uh, is the first step that we're going to discuss. So there are few things that we need to consider when we have to collect the data. The best is when you start with the data collection pipeline, start with only few features, maybe one or two features that will help us confirm that model works as intended or not. And once you have built your baseline from a couple of features, you'll feel like, okay, I'm making some progress, right? But we also need to understand in terms of data, right? What is, if you put in the garbage, if you put in garbage, it's gonna throw out garbage. So garbage in, garbage out. It's a terminology used a lot in the data space, right? If the data is wrong, what your model is gonna do is also wrong. So there are two. These are the two things, like quality and size, which are going to matter a lot when we think of collecting the data. But how do you measure, like, quality, or how do you improve it? Uh, that's one of the question. In terms of size as well, how much size you should, what's the size of the data you should have? Again, that size also depends on the use case, right? In some cases, if I'm taking example of animal species, right, I don't know, to be honest, don't quote me on it, but there could be few hundred, right? And if you have examples of few hundred, that's enough. But if you're talking about Google, say, smart reply, if you're building a model for that, I mean, that has to be trained on such a big data source or data set, uh, which is nowhere compared to, say, animal species. So the size of the data set will depend on the context of your problem as well. And in terms of quality, there are a few things we would need to consider, like reliability of the data. And reliability basically refers to, the degree to which I can trust the data. And obviously, as we know, like, if a model is trained on reliable data, is obviously going to give useful predictions. So we must, like, see how common are our label errors. So if it's done by humans, what's the mistake percentage, you can say. uh, if our features are noisy, how much noise you can tolerate in the data, if the data is properly filtered to your problem. So, for example, if you are building a spam detection, would you need data from bots? Yes. Uh, but if you are trying to improve search results for humans, then you wouldn't need uh, the data from bots, right? So, depending on the context of your problem, you'll see if you have the required data or not. And what actually makes the data unreliable are these four things: omitted values. So in case of first example about human data, we were discussing if someone missed adding the data points or enter a value, right? That's omitted value. So you'll see like data has a lot of missing values, and you have to see like whether those could be ignored or is it big enough uh, to term your data as not reliable. Whether there are duplicates uh, in your data, whether there are bad labels. So, for example, a cat picture is actually mislabeled as a dog. How many such cases are there? So those would be a bad label uh, and bad feature values. So uh, when you're collecting, say, readings, someone by mistake added a zero at the end, and it completely changed the meaning. So those are bad values. So those things actually make the quality of data unreliable, and something we have to like be very cautious of. Another thing is like whether you're going to get good results on training versus your prediction, and whether it's going to cause skews or not. Whether you have good feature representation, uh, that means the data that is shown to the model, is it does that represent all the features? Is that normalized? Are we handling the outliers or we are not handling the outliers? Uh, those are the things also we need to consider. And as I did said, training versus serving skew is also because these are the things that's gonna impact the quality of your data that you're collecting for the model. And during training, like just use the features that will, as I mentioned earlier as well, just use the features that will be available when you're actually going to serve the data to the model as well. So minimize that skew. Once we've done that, we have to identify labels and sources. uh, so when your labels are well defined, it makes job of ML model much easier. We've discussed about proxy labels and direct label. So obviously the best scenario is if you have best direct label available. For example, are you a Virat Kohli fan? Are you uh, did you like would you recommend the video, right? Those are like direct labels if you're getting the value directly from the systems, right? So if someone has this flag of yes, I am Virat Kohli fan or no, I'm not, right? So those are like very easy to catch, but that's not always the case. So you might as well see are there other signals which will help us uh, identify if the person is Virat Kohli fan. Maybe person is watching a lot of old videos of Virat Kohli, following Virat Kohli on Instagram, liking his photos and all that. Those are like good proxies or indicators if someone is a Virat Kohli fan. So those would be considered as derived uh, variables rather than a direct so derived labels rather than a direct variable direct label. So and label sources. So if we have direct label for events, that means if the user did the user click the top search result, that is a direct label that is available for event that is happening, or for an attribute. Will the advertiser spend more than whatever dollar amount in the next week? Those are for the attributes. So it's critical to identify the labels and the sources, uh, and also direct labels that are needed for the past behavior, right? how much time a person has spent watching Virat Kohli's old videos, right? Those are the past behaviors. So we need, direct labels uh, of that. Uh, so that will be used for supervised machine learning to make predictions. So you would be using that and identifying, okay, can I use that as my data and my length of, say, how many hours a person week on a week spends on Virat Kohli videos as my label, and treat it as a supervised machine learning model. But there are always cases when you don't have access to all that data. Then what do you do? Maybe heuristic would be an approach where you launch based on heuristic approach for the first launch, and then as you gather the data, you learn more about it, then you train the system on log data. You can use logs for a similar problem, or you can even use like human people initially to generate that data or label that data. But over time, once that is done, your data set would be rich enough. And obviously, there are pros and cons of using human level data. Human raters, we know they can perform a wide range of tasks. Uh, your data forces will, you have to have a clear problem definitions, but it's also expensive, you know, and it requires multiple iteration. So some things to consider uh, when you don't have the enough data to log. But there are cases when you have too much data as well. And this is what we're going to discuss in next is, which is sampling and splitting. So when we have a lot of data, obviously you can't use that entire data to run through a model because it's going to make it so expensive, and it's going to consume so much time that it's it cannot be used in production setting. So that's where like sampling comes into a picture, where we select the subset of data, and we use that as a sample to be fed to a model, and model gets trained on that. But and there are various ways how do you select that subset. It could be a random uh, queries, random sessions. It's random splitting methods, different ways of sampling the data, which I'm not going to cover in detail here, but there are different ways. All we have to also consider, and are there any filters that we need to apply uh, for for that subset of data. For example, I don't want to include any PI information because when put in production setting, I might have to filter any PI data. So you would want to keep that out of picture when you are selecting it. Uh, so these filtering are helpful. Uh, and then next comes the concept of imbalanced data, right? Imbalanced data is when you have one category is represented heavily and the other category is represented in minority. So there is a skewness that happens. So when a classification data set gets skewed like this in terms of class proportions, we call that as imbalanced data set. And the class that has the larger proportion of the data set will be called a majority, and the smaller proportion would be called minority. And there are different techniques to handle it, and there are different, I would say, degrees of imbalance as well. uh, that would be there in your data set. It could be a mild imbalance, it could be a moderate, or it could be extreme, and the steps you're going to take to tackle those would be different as well. So mild could be like maybe 20 to 40% of the data set uh, is minority. Moderate could be 1 to 20%, and extreme could be less than 1%. So it could it could vary. uh, but you need to understand the that if the data is imbalanced or not. um, if we take an example of fraud, right? How many fraud happens, credit card fraud happens, if I look at all the credit card transaction in a day? Maybe 0.022%, something like that, zero point 0.2. So clearly we have imbalance there, right? So when the if you feed this data as it is to the model, it gets very difficult to identify because there is false uh, category which will have very less representation or proportion, but the true would, sorry, the other way around, false would have more and true would have less. So we have to understand that we tackle the imbalanced data. And there are different techniques. Downsampling and upfading are two steps that you would perform. So in the downsampling, you would downsample the majority class. So you can downsample, say, majority class in this case, which is false, by 30, by 40, depending on how you want to do it. And that will bring down the positive to negative or true to false ratio down, uh, which is still imbalanced, but I would still say much, much better than the original imbalanced proportion. Then you would upweight the downsampled class. So you have downsampled the majority class, then you were gonna apply weighting to it. So you add weights to the downsample class, uh, and then you think, why would you want to add weight, right? Weight will define how the model treats that example. So if I apply a weight of 10 or 20, the model is going to treat that class or the examples to which the weight is applied 20 times more important uh, than an example weight of say 1, right? So this is required or this is done so that there is faster convergence in terms of disk space. You have by consolidating the majority class into fewer examples, but with higher weights, you're spending less disk storing them. Um, so the minority class gets more disk space and greater number as well. And it's also used helps in calibration. So downsampling and then upweighting is a technique you would apply to handle the imbalanced data. Then comes splitting. Uh, again, splitting the data into test, validation set, and training set uh, is what you're going to perform. Training set is what your model is going to get trained on, and then validation and testing set are actually kind of validation would be what you're going to validate your model after you have trained it, and then you're going to test it on the testing set. And that proportion is the way you split the data. There are different ways to do it, and it also is on the business problem that you're trying to solve. You have to be thinking about that when you split your data. You can split your data randomly, so they'll have maybe similar kind of, or you hope they'll be representative when you do a random splitting. There are different ways to do split. There is like train test split. There is or there's a k-fold split. There is time series split. You might want to split the data based on say time, which first 30 days or first 15 days becomes your training, and then your 15 days becomes your say validation, and 20 to 30 for one of the month becomes your testing day. But you need to check whether that works for your scenario or not. Reason being, like, if you're doing sales prediction and you see most of the sales happening in the first week, first 2 weeks of the month, your prediction would be wrong, right, for the later half, because you have trained your data on the first 15 days where the sales is gonna be high, but actually on the last week of the month your sales are actually low. Maybe people are running low on money as it is the end of the month. So you have to be careful when you're doing this split. As I mentioned, it depends on the use case. Uh, and as a train test split is another approach where you randomly take a proportion of data and set it aside for later testing. And k-fold is another mechanism where you're using all the data points in your data set for both the training and test data. So these are different approaches to splitting your data, and there's a lot of material out there. You could read about it. I mean, this could go much in detail as well. And then comes the transformation of data. I know we are running time, so I'm just being quick as well. When we are transforming the data, this is the key step that comes, which is feature engineering. Feature engineering is basically the process of determining which features might be useful in training model and then creating those features by transforming the raw data. Sometimes those features might not be directly available. You might need to convert a categorical variable to a numeric variable, or do some other transformation to extract those features. Features are nothing as we discussed in the weather app, right? The day of the month, is that a better is that a feature that you're going to use? Maybe not, or day of the week. But the dew, the temperature, uh, those could be the things that you might use as the feature. So, and then you're going to transfer some of those things, right? Into, if there's a categorical, you'll convert it into a numerical variable or numerical feature. So that's the entire process of determining what features you're going to use and bringing them into the shape and form which works for the model is the process of feature engineering. And in terms of engineering, there are some mandatory transformation you're gonna perform so that your data is compatible for the modeling purposes. And there are some optional as well that you can perform. So mandatory would be like converting non-numeric features into numeric. Obviously, because you cannot do matrix multiplication on a string, so it would convert all the string values to numeric representation. Uh, you might as well do like you would also do like resizing inputs to a fixed size. An example would be, say you have an image model, so you would reshape all the images on the same, in the same fixed size. So so that your inputs become of the fixed size. So these are some of the mandatory transformations you would perform. There are some optional like normalizing the numeric features so that your model performs better. And all of these like optional, I mean we would call them as quality transformations because they are there to improve the model accuracy or quality so that it gives better result, and it's these are not like mandatory transformation uh, to run the model. You'll be able to run it but maybe not get better results, but mandatory one you would have to do it so that you are able to run your model. And where do you transform? You can apply your transformations while you are generating, while you are doing the modeling process, or even before like you've generated, you're into the training process. So in the transforming which is done prior to training, we apply the transformation before any training process is applied. Obviously there are pros and cons in terms of this approach. It is done only once then. So you can look at the entire data set to determine what kind of transformation the data would need because you're looking at the entire data set. But again, your transformation need to be reproduced when you are actually doing the prediction. So there could be a skew that could happen, which you need to be aware of. And any transformation that require that changes that would come in, it would require rerunning the entire data generation process. So that could lead to slower time or slow, process. So these are the things you need to consider. Skew is actually dangerous as well. So as I mentioned, something to consider of. And you can also transform within the model, right? They that happens like as part of the model code, you're doing the transformation there and then. Uh, so model takes in the untransformed data and will transform it as part of the model. Uh, there are benefits. It's easy iterations. If you change the transformation, you can still use the same files, same transformations at training and prediction time you're going to get. But these are expensive, and it could, because it's done as part of model, it can increase the time the model takes to complete. So some of those considerations, and as part of like transforming, not transforming, I would say, but uh, something that you should keep doing regularly is keep exploring and visualizing your data as well. Uh, for example, visualize your data, say by using scatter plot, histogram, uh, to throughout the transformation, as you would do it as part of your exploratory data analysis. You would, I would suggest, also do it as part of transformation, because it helps you continuously check your assumptions, or if there are major changes that has happened in the data, it'll show up when you are transforming the data if you keep visualizing it as you go. So those are some of the points on transforming your data. And there are a few techniques you could use to transform the numeric one. I know we're short of time, almost done, but I'll quickly run through some of these techniques. So we want to normalize the numeric data to the same scale as other numeric data. That's one of the transformation we would do. For example, city population, that could vary a lot, right? If I compare, say, New Delhi with a small town anywhere in India, right, there would be a vast difference between city population. So we want to normalize that as well. So it's a good choice. We could do a linear scaling. Linear scaling is a good choice when you know the approximate upper and lower bounds, and the data is uniformly distributed, right? And then you can also apply feature clipping. So if your data set has extreme outliers, you can apply that. So if the values are like 100, where 100 is an outlier, you can say anything above 50, consider that value as equal to 50, right? So temperature cannot go to 100, and that's an outlier, right? But 50, maybe that's a possible scenario. We get that in India. So that's feature clipping. You can do log scaling, as we all know. It will compute the log of your values to compress like a wide range to a narrow range. So that's another approach you can do. Or the final is z-score, which is used a lot as well. So it's a variation of scaling that will represent the number of standard deviations for the mean. And I don't know if you have done modeling or you have done exploratory analysis and brought the data into a normalized form. This is one of the techniques we all use quite often. And then you can also perform bucketing for categorical when we want to transform numerical data to categorical data. Bucketing is like temperature being 0 to 5 degree, 5 to 10 degree, things like that. So you build buckets, uh, and you can build buckets with equal boundaries, which is equally spaced boundaries. So, or you could build buckets with same number of points rather than this equally spaced boundaries. So in the same number of points, the boundaries are not fixed, but the number of values that are going to come, or number of points that are going to come in that boundary, is going to be the same, because sometimes the data is not that distributed that all the values, if you equally space it, although you are representing all the values. So these are some of the techniques you could apply for transforming the data, numeric data. Uh, and I know like we are just over time, but I had this much to cover. I know I ran quickly in the last few steps, uh, but these are the things I wanted to cover today in the first part of the series. I want to open it to any Q&A, and if you're not able to take it now, feel free to reach out to me as well for any Q&As. Okay, that's it from mine. Feel free to connect with me on LinkedIn if anyone wants to reach out on any questions. Be happy to talk about it. I will leave that. I've already shared with the host the PPT, and maybe they can share it.
Yes, sir. Yeah.
Yeah. Okay.
Thanks a lot, Rishabh. On behalf of Analytics Vidya, I would like to thank you for your time and for delivering such a wonderful session. I'm sure our
Okay.
audience found it insightful, and hopefully we can conduct more sessions with you. The LinkedIn profile of the speaker is in the chat description. If I hope you have guys have filled in the feedback form. I request you to please fill in the poll about feedback as it helps us to conduct such more sessions. If you wish to conduct a webinar or are facing difficulty in registering, connect with us at data@analyticsvidya.com. The recording of the session will be available within 2 days on our YouTube channel, whose link is in the description. We will be back with another session of data tomorrow. The link is in the chat session. Till then, bye bye and keep learning.
Thank you.
Thank you, sir.